Let me define for you a very helpful problem-solving technique known as the parallel axis theorem. So the moment of inertia from some arbitrary parallel axis is the moment of inertia of the center of mass plus md squared. So the d is going to be the distance from the center of mass to some arbitrary parallel axis. The axis is going to be parallel to the center of mass axis about which the object would rotate and which we know the moment of inertia. So let's try it for the rod that we had before. So the center mass, pivoted from the center mass, we know the moment of inertia of that is 1/12 ml squared. We derived that. We solved for it. We also solved for it rotated about the end. But let's now move it from the center of mass, L over 2, to this new axis pivoted about the end, and that is parallel to the axis we just had. So the d factor is L over 2. That's the d. So the moment of inertia pivoted about the end is the moment of inertia of the center of mass plus md squared. But d is L over 2. So this is 1/12 ml squared plus 1/4 ml squared, which is 1/12 plus 3/12 ml squared, or 4/12 ml squared. The moment of inertia of the thin rod pivoted about the end is 1/3 ml squared, which is exactly what we discovered through a much more laborious effort. And so you can see that this could be very useful, especially if you know the moment of inertia of the object about the center of mass. And typically you will for simple geometries. And that's essentially all that we're going to be dealing with anyway. Let's now use the parallel axis theorem to look at the moment of inertia of a solid disk rotated about its edge. So it's not going to be rotated from the center of mass, which is right here. This is the axis of the center of mass. We're going to rotate it about its edge here. So the moment of inertia, the center of mass, as we know, is 1/2 mr squared. The moment of inertia of the parallel axis, notice this is parallel to the center of mass axis, is moment of inertia of the center of mass plus md squared. And in this case, the distance from the center mass to the parallel axis is d. So the moment of inertia pivoted about the edge is 1/2 mr squared plus md squared, where d is r. So we have mr squared, and that's 3/2 mr squared. Now before we just consider anything else, we must pause for a moment and ask ourselves, assuming we've been paying attention to the content so far, I thought you said that the highest the moment of inertia can be is mr squared. Well, I did say that. So how do we square that with this thing being 3/2 mr squared? Well, if you consider carefully what I said, it was the fact that the highest the moment of inertia can be when rotated about its center of mass. So the resolution, the reason why the moment of inertia of this object can be 3/2 mr squared, actually a greater moment of inertia than a thin-walled cylinder, is because we're not rotating it about the center of mass. We're rotating it about the edge. So if you think of the integral of r squared dm, you consider that the radius, the average radius of where the mass is on this, pivoted about here, is significantly larger than it would be if you were rotating it about the center of mass. So it's got, the mass is essentially extended further out, and that has a huge effect on the center, on the moment of inertia. That's why you can take a point mass and put it way out a long ways away, a point mass with a large radius, and just simply have mr squared for the moment of inertia of that point mass. And if r is it can be arbitrarily big depending on how big you make r. So hopefully that makes some sense out of this. Well, departing from the parallel axis theorem now, here's a fun problem to solve. Good problem in AP physics. So we're going to have a uniform disk pivoted from that is a flea at radius r. And that flea is really attached to that disk. It has mass m. The initial angular velocity is 0. The whole system is now going to be released from rest, and when the flea is at the bottom, what is its angular velocity? And that's exactly the sound that you're going to be making when that flea starts penetrating your throat. So the total work is delta K. This is an energy problem again. And so let's kind of start it the way we did the last one. We have K2, kinetic energy there at the bottom, is UG1 up at the top. Just kind of cutting to the chase here. So 1/2 mv squared. Now that's a translational expression. So that's the speed of the flea at the bottom, 1/2 mv squared. There's other ways to do this, but that's how I'm going to do it. But is that it? No. You know that the whole disk is rotating, so we have 1/2 I omega squared equals mgr, r being the height lost in rotating from 3 o'clock to 6 o'clock. So 1/2 m. Now v is omega r, so we have omega squared r squared plus 1/2 of the moment of inertia, which is 1/2 mr squared, solid disk, times omega squared, equals mgr. A lot of stuff divides out here, so let's go ahead and do it. The m's go away, and r goes away in each term. Thankfully, it makes us very happy. At least it does me. So now we can factor out an omega squared. We have 1/2 r plus 1/4 r equals g. So that's 3/4 omega squared r is equal to g. And from this, we get our coveted expression. Rad 4g over 3r. Now, don't go to sleep on me. We're going to figure out the moment of inertia for a uniform sphere. You can think of this as a challenge problem, but it's not so bad. Just stick with me here. So we have a sphere shown. We're going to divide the sphere into an infinite number of solid uniform disks, each of radius r and thickness dx. So let's insert one. There it is. Oh, now you're getting the perspective. There's a disk within the sphere. Now this guideline is supposed to be an axis that's going through the center of everything, but hey, I drew this in PowerPoint, so it's hard to show the perspective correctly. Going through the center of this disk, this part shouldn't even be shown until it emerges out of here. Anyway, that's going through the center of the whole contraption, even though it doesn't look like it. Now, this radius big R is from the very center of the sphere to the edge of this particular disk. This radius, little r, is from the center of the disk to that same location. Therefore, this is a 90-degree angle. And now we have, between these two starting points for the two different r's, x. Hopefully you can make sense of it now. So this particular thin disk is located x from the center of the sphere. That's where it is. And the thickness is dx. And the mass is dm. So as you can probably imagine, we're going to take a whole bunch of these, infinite number of infinitesimally thin disks, and fill up this whole sphere. All right, so the moment of inertia of a disk, 1/2 mr squared. R, thinking of the geometry here, this is the hypotenuse, this is one side, this is the other side. So let's use Pythagorean theorem. So R is rad big R squared minus x squared. dV is the area, pi r squared times the thickness dx. So that is, recognizing that R is square root of r squared minus x squared, r squared is just big R squared minus x squared. So that's our dv. dv is pi times this dx. So then dm, which is rho dv, we can expand that to rho pi times big R squared minus x squared dx. And then di, differential moment of inertia, is 1/2 r squared dm. But dm is this rather expansive term we just derived. So that's 1/2 big R squared minus x squared rho times pi times r squared minus x squared dx. And this whole part here is just dv. So that's all dv, rho dv. Okay. And now let's continue on with this. So this differential I is, we had the half, so rho pi over 2. And we had big R squared minus x squared twice in that previous expression. So this quantity squared dx, simplified. Therefore, the moment of inertia of the sphere is the integral of all those di's from minus r to r. Since we started x is equal to 0 in the center of the sphere, now we can just go from 0 to r and double the whole thing. And that'll be a little bit nicer because, look at that 2. That 2 and this 2 will cancel. And so we get rho pi integral from 0 to r of r squared minus x squared squared. So we have to expand that. It's not a whole lot of fun, but there it is. Not too bad. And when we integrate this, of course, it's with respect to x, so we get an x here. We get x to the 3rd over 3, x to the 5th over 5. So there it is. And now every time we see x, we stick in r. And when we do that, we're going to get r to the 5th in every single term. So we can factor out that rho pi r to the 5th. And we have 15/15 r to the 5th. Here we have 10/15, and here we have 3/15. Well, 15 minus 10 plus 3 is 8. So we have 8/15 rho pi r to the 5th. And we could stop there, but not quite, because we need the moment of inertia of the sphere in terms of the mass, not the density. So let's finish it up. So let's translate the density into mass. We know the mass of a sphere is rho v, and the volume of a sphere is 4/3 pi r cubed. So the mass is going to be the density times the volume, rho 4/3 pi r cubed. Well, the result we got was 8/15 rho pi r to the 5th. I'll bet you see something potentially factoring out here, namely the mass. In fact, we can write this as 4 times 2 over 3 times 5 rho pi r to the 3rd r squared. And now you see the revelation of the mass factored out of this moment of inertia of the sphere, giving us our coveted result, the moment of inertia of a uniform solid sphere, 2/5 mr squared. Oh, come on, get that stupid flea out of here.